Like we have these three, in particular, we are taking three equations. So these are the unknown like x, y, and z, and a1, b1, c1, d1 are known to us. And we have to find the x, y, z such that they satisfy these three equations. So in this case, if you remember your Gauss elimination method, what we do, we actually this eliminate x from the first two equation by like removing the first coefficient like this, and then this 2 equation 2 minus a2 upon a1 into 1, and equation 3 minus a3 upon a1 into equation 1, and this will give us this equation. And later we will remove this also. So to remove this one from the third equation, we will do this equation 6 minus b3 dash upon b2 dash into equation 5 will give us this one. And then you go for back substitution, like from here you can calculate z, and then you substitute z in this above, then you will get y and then x. So this is like when we do this by like manually through equation and equation. Now we can solve this also by using augmented matrix technique. In this, what we will do, like if you remember your BTech first semester, we have this is your system of equations, and we can write this system of equation, its corresponding equivalent metric equation like this. Here a1, b1, c1 are row, and then you multiply to this column, you will get the first column, this one, and then this one is equals to d1. So from the knowledge of matrix, you can you know that this three system of equation can be rewritten as in this matrix form. So this is a matrix, this is x, and this is d. Sometimes we represent this by capital B also. So this is the way we write our augmented matrix. In this, what we do was first we write the matrix A as it is, and then we draw a vertical dot line like this, and then we write the entry of the matrix D, and this is our augmented matrix. And then we reduce this augmented matrix into echelon form, and in echelon form what we do, like this is our A11 entry. This is our, like if we assume this is a matrix, and representing this is A11 equals to A1, A12 equals to B1, A13 equals to C1, and A14 equals to D1. Similarly, here you can also write like A21 equals to A2, A22 equals to B2, A23 equals to like C2, and A24 equals to D2. So if we are representing the generalized entry of this matrix Aij, where I is ranging from 1 to 3 and j is ranging from 1 to 4, and then we know that these are the diagonal entry, this, and this. And in echelon form, what we do, this is our first diagonal entry, we try to make 0 below it, and then this is our second diagonal entry, we make 0 below this. And if our entries below the diagonal elements are 0, then we say that our matrix is in its echelon form. So here this is our augmented matrix, a vertical dot line D, and then we apply our elementary row operations, and finally we have this kind of matrix. If we have this kind of matrix, then we say that this is in the echelon form. And then again by back substitution, like from here we can get z, and then after substituting value of z we get y and then x. So this is one problem related to this. Like this is our system of equation, and we want to solve the system of equation using our Gauss elimination method. Then here he is doing like it. This is equation 1 and 2, and then minusing them, and then try to eliminate x from the equation, and we have this. And then we remove y from 4 and 5, we will get z. And once we have z, this is substituted in this one, you will get your y. And then y and z, substitute in any one of them, you will get your x. So we'll see this procedure with in matrix form, like the same system of equation we have rewritten as this: x plus 3y plus 2z equals to 5. And here I think he changed the row, interchanged the row. Okay, actually in this second equation, you can see we can divide it by 2, because 2 is the common factor in left hand side and right hand side. So we have this equation is equivalent to this equation 2, x plus 2y minus 3z. So the matrix equation corresponding to this system of equation is 1 3 2, 1 2 minus 3, and 1 5 3, and this D matrix is 5 minus 2 10. So this is. Now you use your elementary row operations to make 0 here. So you know that here already 1 is there. So if I do the elementary operation like R2 goes to R2 minus R1, this one, in this matrix, if I apply this elementary row operation, R2 goes to R2 minus R1, and R3 goes to R3 minus R2. So I will get 0 here. And the second is, this is the diagonal entry A22 of the matrix A augmented B, and I have to make 0 here. So I apply the operation, this one, R3 goes to R3 plus 2 R2, and we have 0 here. And then we again rewrite the matrix equation corresponding to this augmented matrix, and we will have this one. One more thing you have to notice this: if you are using this procedure, you are allowed it to apply only this elementary row operations. If you apply any column operation, then your coordinate will change, like, because we know that this is corresponding to like here x, y, and z. But if you apply column operation, then simultaneously your x and y, z also move, and then it's a trouble. So don't apply any column operation when you are converting your augmented matrix, its corresponding equivalent matrix. So this thing you have to remember. So here you are not allowed it to use elementary column operations. So this is, if you applied, then the role of x and y and z are interchanged. Like if you apply any column operation, then z and y are interchanged, and that will be a problem. So the corresponding equivalent system of equation corresponding to this augmented matrix is this one. And then you go for back substitution, like here, from here you can get z. Then you just substitute z here in B, you will get y and then x. So you try this method to solve this equation. This is again a well-known method to you also, Gauss-Jordan method. So Gauss-Jordan method is a modification of Gauss elimination method. In this method, the elimination of unknown is performed not only in the equation below, but in the equation above the, and also reducing the system into like in a diagonal matrix form. So earlier what we are doing in this echelon form, we are transforming this matrix into its echelon form. But if we transform by using elementary row operation into its corresponding normal form means this is a diagonal matrix. If we get this in the form of diagonal matrix, then this method is known as Gauss-Jordan method, like this one. So you apply elementary row operations, and you have to reduce this into this one. And if you are able to reduce this, then after, like, if we are here, and we can write again, use we can one operation, like r1 goes to 1 upon a1 in r1. So if r1 goes to 1 upon a1 r1, this is 1 0 0, and r2 goes to 1 upon b2 r2, this is 0 1 0, and r3 goes to 1 upon c3 r3, this is 0 0 1. So it is finally reduced to a identity matrix. So if your A matrix of the augmented matrix A vertical dot D is transformed into a diagonal form, or its normal form, like in identity form, identity matrix, then we again, from the augmented matrix, we can get their corresponding system of equation, and we get the value of x, y, z. So this procedure is known as Gauss-Jordan. In this Gauss-Jordan method, you have to apply your elementary row operation to reduce the matrix A of the augmented matrix A vertical dot D to its corresponding diagonal form or identity matrix. So we'll see this one. So if you have this system of equation, like x plus yz equals to 9, 2x minus 3y plus 4z equals to 13, 3x plus 4y plus 5z equals to 40. So if we have this one, then how I reduce this one, or how I get the solution of this system of equation using Gauss-Jordan method. So I write this three equation into corresponding matrix equation, this one. So this is the matrix form of the system of equation, and then I write its augmented matrix. Augmented matrix is this. So here this matrix is B. So A vertical dot and vertical dotted line, and then matrix B, and this is our augmented matrix. Now in this, I have to make first 0 below the diagonal element, because this is A11 entry. So if I am representing this augmented matrix by generalizing, generalizing index Aij, I was ranging from 1 to 3 and j is ranging from 1 to 4. Then I have to make 0 below this one entry, below this entry, and below this entry, and above also. If I able to succeed to make 0 above and below the diagonal entry, then the matrix is reduced in its diagonal form, and then we can reduce into its equivalent identity matrix by dividing the corresponding entry, and then we will easily get our solution. So we'll see. So first job is to make 0 below this A11 entry. This is A11, the first diagonal entry of the augmented matrix A vertical dot B. So to produce 0 here, I am using these two elementary row operations. R2 goes to R2 minus 2 R1, and R3 goes to R3 minus 3 R1, which is getting 0 here. Now I have to make 0 here. So to produce 0 here, again I have to use this row operations. So if I use, okay, even though when this course is taught to you in your BTech first semester, like how to make 0 below this entries. So there the corresponding faculty told you that if this is the R1 row, and we are making 0 here below the A11 entry, so to make 0 below the A11 entry, we use the R1 row. Like you can see here, R2 goes to R2 minus 2 R1, and R3 goes to R3 minus 3 R1. So if you follow this standard procedure, like to make produce 0 here, I will use the row R1, then you easily get this 0 here. Similarly, to make a 0 below this entry, I have to use, because I am creating 0 below this entry. This is R row entry A22. So to make 0 below this entry, I have to use R2 row. Because if to make a 0 below this entry, like this place, if I use R1 row, so then this 0 is disturbed, because here some non-zero entry will occur. So to produce 0 below the A22 entry, I have to use R2. So like here you can see, to produce 0 at this entry, so I use this operation. R3 goes to R3 minus R3 plus 1 upon 5 R2. So to make 0 below A22 or to make 0 above A22, I have to use R2 row. If I use any other row, it will disturb my other 0 which are already produced. Similarly, to produce 0 here, I have used this R1 goes to R1 plus 1 by 5 R2. So this is 0 here. Now here this is your A33 diagonal entry, and this diagonal entry below there is no equation, so no need to do anything, but above there is non-zero elements. So to produce 0 above A33 row, because we have already produced these 2 0 in the third row, so to produce 0 above the A33 row, I use this row. If I use any other row, then this 0 may be disturbed. So to produce 0 at this place, I will use that row 3. So to get 0 here, like R2 and R1, so R1 goes to R1 minus 7 upon 12 R3, so I will get 0 here, and 5 upon minus 5 upon 6 R3, I will get 0 here. So like this I am getting. Now this is a diagonal form of the corresponding A matrix of the augmented matrix A vertical dot B. So once your system, and again you have to notice this, you are allowed to use only elementary row operation. If you used any column operation, your results are wrong. So using your elementary row operations only, you have to reduce the A matrix of the augmented matrix A dot B into its corresponding diagonal form, and then you rewrite your system of equation from the reduced form. So if I write the system of equation, I will get x equals to 1, minus 5 equals to minus 15, and 12 upon 5 z equals to 12. I will get x equals to 1, y equals to 3, and z equals to 5. So this is the Gauss-Jordan method to solve the system of equation. So till now what you have learned, this Gauss-Jordan and Gauss elimination method, here we are getting exact solution. So we are not, they are actually exact, not the approximate solution. But sometimes we have so many like number complicated equations, or like more number of equations. Instead of 3 we have 10 or 11, so this procedure is difficult. So we have another methods. So one of them is factorization method. So in this factorization method, we have considered this is the our again system of equations. Here A11, A12, A13 are known, A21, A22, A23, A31, A32, A33 are known to you, B1, B2 are also known, and unknown variable here are x1, x2, and x3. So you have to find three values of the unknown variable x1, x2, and x3, so that they satisfy this equation. So again in this factorization method, we write this system of equation into corresponding its matrix equation. This is A matrix, this is X matrix, this is like containing the unknown variables, and this is matrix B. So in this method, the matrix A is to be written as a product of lower triangular matrix and an upper triangular matrix. So like what we do here, this is the A matrix and we write this A equals to L into U. Here L is a lower triangular matrix, that is the entry below above the diagonal element are 0, and U is a upper triangular matrix and it means the entry below the main diagonals are 0. So we have to find matrix L and U such that the product of L and U is equals to A in the factorization method. So in this factorization method, we are actually factoring this matrix A as a product of two matrices. One is L, another one is U. So this is your L and U. So the type of L and U are this kind. Like L is all entries of the main diagonal element are 1, and L21, L31 and L32 we have to calculate. Similarly, this is upper triangular matrix U. So here the U11, U12, U13, U22, U23 and U33 we have to obtain, and the entry below the diagonal elements are 0. So we have assumed that this is our A matrix of the matrix equation AX equals to B. So this A matrix is factored into two matrix L and U. L is a lower triangular matrix, this one, and U is a upper triangular matrix, this one. And here the small l ij and small uij we have to calculate. So how we'll calculate this, we'll discuss. First, like if we do, so what are the benefits we are getting from doing this? Like because now we have, if we find L and U such that, then A is equals to LU, and in the matrix equation AX equals to B, I can write LU because A equals to LU. So LU, this is A, X equals to B. So first I solve this equation like ux equals to b, and then luv equals to b. So ux, I assume like after multiplication ux, I will get another matrix v, and this v again I write like v are like unknown variables, like I'm saying v1, v2, v3. So this is matrix v, and then because now ux equals to v, so I write v here and I will get lv equals to b, and then I will solve this equation. So from here I will get the values of v, and then I substitute the values of v here, then I will get the values of x. So like if I am having all these allies are known to me, then v1 equals to b1, v2 equals to like this one, and after simplification, similarly b3 can be calculated from these three equations. So v1, v2, v3 can be obtained easily from this three equation, and then the values of v1, v2 is known to us, and then we substitute in ux equals to v equation like this one, and then from here I will get x, and then x3, then x3 I will substitute here, I will get x2 and then x1. So the main task is to find this L and U. So we assume that this is L and this is U and this is A, and L into U equals to A. So multiplying this, because this is the matrix product, so if we multiply, what we will get? 1 is multiplied to U11, and because others two entries are 0, here the two entries below are 0. So if this first row is multiplied to this first column, you will get u1 only, and then u1 is equals to your a11. Similarly, this first row is multiplied to the second column, you will get u12, and the first row is multiplied to the third column, you will get the u13, and they are all equal to this. u11 equals to a11, u12 equals to a12, and u13 equals to a13. So once now you know the values of u11, u12, and u13. So it is like Whatever the entries of A matrix, A11, A12, A13, they are actually U11, U12, and U13. So U first row of U is easily obtained. Now to get the second value like L21, because I have to calculate this L21 also. So what I do, multiply this row to this column. So if I multiply this row to this column, I will get L21 into U1 equals to A21. So from here, because U11 is already obtained in the previous step, so and A21 is known to us, so L21 is equals to A21 upon A1. Similarly, to get this entry, I will multiply this to this row, column, first column. So I will get L31 U11 equals to A31. So this is the entry like L21, L31 are obtained because A21, A11 are known to us. So this is these unknown values are known to us and these unknown values are known to us. Now these three and this one is remaining. Again, next step I multiply this L21 to the second row, second column, second row to the second column. If I multiply second row to the second column, I will get this one. And here again, this U12 is known to us, it is A11. L21 is known to us because in the previous step. So from here, U22 is equals to this one. Similarly, you can calculate U3 equals to this one. And then you multiply the second row to the third column. If you multiply second row to the third column, you will get this equation. And here again, this U3 is known to us because in the previous step U3 is there. U13 in the first step is with us and L32 is also here. So we will get U33 also. So this is the procedure like for how we calculate the values of U. In first step, we calculate first row of the U, then we have calculated first column of U, then second row of U, then second column of L, and then third row of U. So this is the procedure to obtain the values of Lij and small uij. So we'll see through this through one example. So this is our system of equation 3x plus 2y plus 7z equals to this one. And this system of equation we have to solve with the help of factorization method. So here we write A matrix is this one because 3, 2, 7, 2, 3, 1 and 3, 4, 1. So this is the A matrix of the system of equation and this A matrix is factorized into L into U. So this is L and this is U and you know what is the procedure we have learned. The first row is equivalent to this the A matrix, first row. So it means U11 is 3, U122 is 2 and U13 is 7. So the first step is easy. Now to calculate the second, so again this is multiplied to first column. L21 into U1 equals to 2 because this is 2. L21 into U11, then you will get 2. And similarly, U11 in the previous step you have already obtained. So L21 is equals to 2 upon 3. L31 into U11 like this is multiplied to this one and it is equal to 3. And then you substitute the value, you will get L31 equals to 1. So this is U13, L21 and 31. And then you will calculate like you multiply this to this one. So this row is multiplied to this one, you will get this U22, U23 like this. So after all this calculation, you will get your L and U. So once you have your L and U, you have to solve first Ux equals to V system. And here you have to assume V like the unknown variable V1, V2, V3. Sorry, first we write like this Lu equal Ux equals to we will write in this A. So this is L and this is U and here will be x equals to b. So first we write this u into x equals to v. So we'll get L into v. This is L into v equals to this b. And then because this is already in the form of lower triangular matrix, and then with the help of back substitution you will get v1 v2 v3. So once you have v1 v2 v3, then you solve this ux equals to v system. So this is u, then you here x, and the v is already obtained. These are the v's. So v, and this is u, and this is x, and then you write in again, write in the from this matrix you can write system of equation, and from here you can get z equals to 1 by 8, and then by substitution you will get y and then x. So this is the way you use your factorization method to solve your system of equation. So this is the way we solve system of equation, and all these method will give you like exact solutions. Tomorrow, like we will solve the system of equation using like iterative method. Iterative method, you know that we will get approximate solution. So like if you have solved this system of equation, this one, and you are getting the exact solution like this: z equal to 1, y equal to 2, and x equals to minus 3. So instead of that, you will get 1.11, 2.23, and 3.001. So it means that if you substitute the value of xy, those approximated values of xyz, you will not get exactly 5. You will get 5.001 something. So we will discuss this tomorrow. So, and if you have any question, you can ask. One more thing, today I am giving attendance to all of you. So if there is nothing to ask, I am leaving. And if you have something, then you say something. So no one is asking nothing, so I'm leaving.